Wait. 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 Okay. This is question set number 9. It's going to use a combination of torques and energy and forces. This is an APC physics question from 1997. So it has a solid cylinder of mass m and radius r rolling down our ramp here at height h, and it wants us to determine the translational speed of the cylinder. There's friction here, so we're allowed to use m, r, h, theta, and g in our answer. So the easiest technique for this is just going to be energy methods. So let's just start with potential energy at the top becomes both types of kinetic energy at the bottom. So we're going to say that mgh, the potential energy at the top, turns into translational kinetic energy in the center of mass and rotational energy. Then we're just going to go ahead and expand that. So instead of writing I, we're going to replace that with the I value of the cylinder, which they tell us in the problem is 1/2 mr squared. So 1/2, let's move that omega over, 1/2 mr squared. And I was going to put the omega squared back here, but really, let's just rewrite it as v squared over r squared. And at this point, we're up with a lot of things canceling. So the mass is going to cancel. The radius will cancel because there's an mr squared, which I wrote wrong there, canceling with this r squared at the bottom. So then we have gh equals 1/2 v squared plus 1/4 v squared. Gh equals 1/2 v squared plus 1/4 v squared, which we just can simplify as 3/4 v squared. So we can just solve for v all by itself, which will be the square root of 4gh over 3. Okay, next is on in our picture, which I redrew here. Please draw all of the forces at their application points. So we're going to draw mg straight down. I chose to draw in the ramp so that I can draw the normal force coming perpendicular from the ramp. And then I'm going to draw my friction force, which I know needs to be up the ramp. And I drew that from down here, so here's my center application. Then it says to show that the acceleration of the center of mass down the sphere is 2/3 g sine theta. So we already have the velocity at the bottom. We know that our object has traveled along the ramp, along the length of this ramp, this distance here, L. So just with a little geometry, we can say that L equals h over sine theta. And then we can just use our kinematics equation, v final squared equals v initial squared plus 2a, and then the length of the ramp, L. But here we have the v final already, and we can square it, so we'll get rid of the square root, and we'll find the acceleration, and we'll rewrite L as h over sine theta. So we're going to have 4gh over 3. The initial velocity was 0, 2, a, and then instead of L, we're going to have h over sine theta. Now to get all a all by itself, we're going to cancel the h's. We're going to divide by the 2, so 4 over 2, that's going to be 2 on the top, 3. We're going to have g still, and sine theta is going to be multiplied to the other side. So bam, we showed the acceleration is 2/3 g sine theta. Now it wants us to determine the minimum coefficient so that it will actually roll. So we're going to have to introduce forces here, which is actually not so bad because that's just a problem we've been able to do before. So we're going to have to break our mg into components because we're rolling along the ramp, so we're going to redefine our coordinate system. So this is going to be now the new x direction, and this is going to be the new y direction. So from here we can sum our forces in the y direction, where when we break our mg up, this is the theta of the ramp. So this here is mg cos theta. So we know then that we're not accelerating in this plane, so we can say that mg cos theta must be our normal force. We can then go in the x direction, and we can say that will be acceleration. We actually know that acceleration, and some of our forces are mg sine theta, this component right here, pulling us down the ramp, and friction force pulling us up the ramp, so that's losing. It's a negative sign. Now we know a, so let's plug in a. So instead of a, we're going to write 2/3 g sine theta. We can solve now for friction force all by itself. My motivation for doing that is I'll set up mu, which has friction force in it. So I'll add friction force to this side and subtract, so I'm going to have mg sine theta minus 2/3 mg sine theta. So my friction force comes out to be 1/3 mg sine theta. Units work out, it's a mass times the acceleration, so that just makes sense. So now I have friction force and normal force. I'm just going to set them up in a ratio. So mu is going to equal Ff over Fn. So our friction force is going to be 1/3 mg sine theta, while our normal force is mg cos theta. So we can see this simplifies to 1/3 and a little tan coming in there. Tangent theta. That's our mu value. Now the last question is weird and conceptual. So they're saying that the mu value won't actually be 1/3 tan theta. It's going to become less, so that they're slipping end rotation. So it wants to know, will the translational speed of the cylinder now be greater? So it says if mu drops, what will happen to the velocity of the center of mass? Will it go up or down or remain the same, and why? So my thought is that if mu becomes less, friction becomes less. So we're just going to slide faster. So I would say the velocity of the center of mass is now greater, because there's less friction force. If we go over to our forces, our friction force has gone down. That would make this acceleration value be able to increase because we have less friction. We still have the same mg sine theta. The friction now will be less than it was, so our ma will be able to be more. It then asks what happens to Ke total. So the velocity of the center of mass will be greater, but what's going to happen to the total kinetic energy? Now remember, the total kinetic energy involves both the translation and the rotation. And so even though our velocity of the center of mass is going to be greater, we're no longer going to be able to say omega times r is velocity. And so we're not going to be able to just know this rotational term connects to that translational one. Our kinetic energy is actually going to decrease. It's going to be less. Because now the friction force won't transform into a type of kinetic energy. Our friction force will become work due to frictional force. And so therefore we're going to lose mechanical energy out of our system. So in our first system we had no loss of mechanical energy, but in this system we do have loss of mechanical energy, and so the energy at the bottom won't just be kinetic energy, it'll be energy and heat from friction. So that loses energy, therefore kinetic energy will be less.